In this section, we're going to look into the technical details about the GANs. So now we are at this point. That is, we are talking about the maximum likelihood method and using the implicit density function, and then so using the direct method. That is, we are going to learn the implicit density function. That is, we do not know the density function. We are using the GAN to learn this function. And now we are going to formulate the problem like this. So we want to sample from complex and high-dimensional training sample distribution. The meaning is that we have a lot of image samples, for example. So we have a space right here. So when we talk about this space, if we are going to plot these samples, and then we come up with a distribution, and then so we would like to draw some samples from this distribution so that we are able to generate some new images. So that is what we want. But this aim is very difficult to achieve. Yeah. So because it is mentioned right here, the training sample distribution, that is too complicated, as well as in a very high dimensional space. It is difficult to just draw a sample from there and then we are going to come up with new image. The proposed solution is that instead of drawing from the complex and high dimensional space, we are going to use a random noise. The idea that is given right here. Generate a random noise according to, for example, the Gaussian distribution, input it into a network. This network, that is to generate from the random noise to some new images, that is, for example, new faces, new digits, that is something like that. That is, again, we would like to use a generator network which receives random noise and then the output is some meaningful samples. This idea, that is very simple, and then we are going to use the terminology we learned from the previous section. That is, we would like to generate some latent code. This latent code is mapped to some new samples. However, this idea, although it is simple, but how do we train the generator so that from noise to meaningful samples? This is also very difficult because we cannot just simply use the supervised learning because we cannot give a label to a random noise. Yeah, and then another one, that is, if the generator doesn't work, that means a random noise will generate a random noise. That means we need to improve this idea so that to make sense of the whole structure of the GAN so that it is able to generate some new samples using random noise. Okay, this is the idea. The GAN structure, we call this is the two-player game structure or arithmetic approach. So instead of only having a generator, we are going to have a discriminator. So we have two main elements. Generator right here, which is going to map a random noise and then into some meaningful sample denoted as GAN. And then so we still have some real samples right here. So we have some real samples, and then so now the discriminator here, that is just to tell you that whether the samples, that is from the real samples, from the real data set, or from the generator. Yeah. So the generator, that is actor, which is going to take action to generate some new samples. The discriminator, this is just to tell whether the sample X right here, that is coming from the real samples or from the generated samples. So that's why we have a switch right here. This switch sometimes can be right here. That means the discriminator will receive a real sample. Sometimes that is right here. So the input will be from the generator. The discriminator does not know where the switch it is. That means it does not know whether the samples, that is from the real dataset or from the generated dataset. So the idea that is we would like to train the generator so that it is able to fool the discriminator, so that the discriminator cannot tell whether this is a fake or real samples. The discriminator that is working in the opposite way, that is, which is able to tell whether the sample is real or fake. Yeah, so that's why this is called a two-pair game. And now with this structure, we just find out that this is a kind of unsupervised learning or hybrid. Yeah, okay. So take a look at the notation or the data structure. Now we have the real sample. If we are looking at this structure, the real samples that is right here. This real sample, which is going to have the density function, we call this is p data. Yeah, so that means right here, as we mentioned before, we have some samples, and then the whole space that is x, and then when we draw a samples from here, we call this is x. X would be one of the image, yeah, one of the images in this space, and then the distribution, the density function of this space, that would be something like that. This line, we call this is the p data. So when we draw a samples from this density function, which will be one of the phases within this space, capital letter X. And now when we talk about latent code, we now move from the real samples to this point, the generator side. Latent code Z, that is randomly draw from this PZ, another distribution, yeah, another data distribution. Usually this is a uniform or Gaussian distribution. It means that Z, that is a random noise. Yeah, so we are going to draw from the Gaussian distribution to come up with this Z, and then this Z will give you the output image or output sample denoted by GZ. Yeah, and now that means up to now we have two kind of sample. The first one, that is the real sample from the real data set, and then the next one, that is the latent code. That is the input to the generator in order to generate the fixed samples. Yeah, and now focus more on the generator. This GZ theta G, that is the function right here. We call this is the GZ theta G. So this is the mathematical model for the generator. Theta G denote the parameters of the generator. In the next slide, I'm going to talk a little bit more about that. So with this mathematical function, this function will receive input Z and then generate the output GZ right here. That would be, this one will have a compatible dimension of real sample. Yeah, so for example, this is going to generate a face, something like that. So the dimension, the resolution should be more or less the same. Yeah, I mean the number of pixels should be the same as the samples right here. Yeah, otherwise the discriminator cannot take different size of the input. Yeah, so once we have this model defined, that means theta G is fixed through the training, and then this data GZ, the phases right here, we have a space right here, we have many phases. So if we are going to plot the data distribution, that would be this PGX theta G. That means subject to different parameters, we are going to have different kind of distribution, PG. Yeah, the ideal case, that is PG, that is the same as P data, so that the generator can produce the same data distribution as the real samples. Yeah, so now the generator, that is the purpose, that is to map the Z space to X space. Yeah, so this is Z, the random noise, the whole space right here, we call this is capital letter Z, and then the output right here, that is the X. Yeah, so we call this is the X, the ideal case, that is this X is the same as this X if the generator is able to approximate or to reproduce the P data using PG. Yeah. And now the discriminator, we are talking about the green guy right here. This is dx theta d. Theta d, that is the parameter of the discriminator. That means the input-output relationship. That would be this mathematical function. When we change the parameter theta d, it will change the output dx. Yeah. So we are going to use the discriminator to tell you whether the input is real or not. That means whether this x is from the real sample or from the generator, using the output dx, which will give you a value in between 0 and 1. 0 denote fixed sample. That means a value closer to 0, it is more fake. When it is closer to 1, it is more real. The extreme case, that is, the dx will give you either 0 or 1. 0, it means that the input right here is fake. 1, that is real. Yeah, so 1, that is real. 0, that is fake. Yeah. So as I mentioned, if we are able to change the parameter theta d, if we are able to adjust the parameter theta g so that P data equals PG, so that means the generator is able to perfectly reproduce the samples in capital letter X space. Yeah. Okay. Now look into a little bit more details. When we talk about the generator right here, G, Z, theta G, that is the generator model. Theta G, that is the parameters. So that means if we are going to implement the generator using a neural network, and then the connection weight would be the theta G. Yeah. When we change the connection weight of the neural network of the generator, it will change the output, the behavior of the neural network. And instead of using a neural network, we can use any mathematical function. Yeah. So, but anyway, we call those parameters theta G, and then GZ right here. That is the output of the generator. That means when we input input Z into this mathematical model, it will produce you GZ. That is something right here. That would be the sample, the generator sample, say phases right here. Yeah. Okay. And now I have a remark right here. So X, say this is X equals GZ. X right here, that is dummy variable. If we are talking about real samples, and then this X, that is from the real sample, and then when we talk about the generator, X equals GZ, X, that is the fixed samples right here. Yeah. And now when we talk about the discriminator, we still have a mathematical function, dx theta d. Theta d, that is the parameters. Again, if we are going to use a neural network, theta d, that is the connection weight. If we are going to use any mathematical model, theta d, just a collection of those parameters. Yeah. So when we input x into this function, which will give you the output dx, that is right here. Again, that is a value in between 0 and 1. 0 means it is a fake image. That means when we input an x right here, this x could be from the real sample or could be from the generator, and then the discriminator will give you a value indicated by dx, that is in between 0 to 1. Yeah. So 0, that is a fake sample. 1, that is a real sample. Our objective, that is to train the discriminator so that the discriminator can tell you whether this is really from the real sample, X is from the real sample, or from the generator. Okay, and now we have a better picture about the notation as well as the GAN structure, and then I'm going to summarize what we have done before. Now, the generator, the input set, that is from a distribution, maybe a Gaussian distribution. This is a random noise. We draw Z from this distribution, PZ, and then that would be a latent. This latent will give you an output X using a generator, the generator mathematical model, that is GZ theta G. Theta G, that would be the connection weight of the neural network if we are going to use the neural network. Yeah, Z, that is the input, and then which once we find the theta G, and then we are able to have the distribution model when we have the Z as the input and then X as the output, and then the data distribution is defined by PGX theta G. So when we change the parameter theta G, the distribution will change as well. Yeah, and now once we fit in the latent Z into the generator, we come up with this X from the generator. So X, that is GZ. When we substitute Z into this model, for example, we have Z1, Z2, Z3. So Z, that is a vector, Z1, Z2, Z3, and then we have the output, that is X1, X2. Yeah, so which form a vector X. But of course, when you look at these images, that is it is not just two elements. Yeah, but anyway, X denote the output of the generator. It is a sample. Yeah, a generator sample. But now, if we zoom into this X, if this is an image, and then we will have a lot of pixels right here. For example, that is 5 by 5 images. And then each dot right here, that is a numerical value. For example, 6 point something. So that means if we are going to use a neural network for 5 times 5 pixel, and then we have to extend it to x25, so that this X will have 25 numbers to represent this image. And now this is the generator, and then don't forget that we still have the real samples. The real sample, that is drawing from the density model P data. This is the real distribution. Yeah, this is the real distribution. So that means now we have the real samples, we have the fixed sample right here generated by the generator, and then we also need to decide the discriminator to tell whether the sample is from the fake or from the real samples. So this P data model, this distribution could be from a data set. This data set, that is for example, many mushroom images, because this generator is going to generate the mushroom samples.